The 360 on Energy and Carbon, hosted by 360 Energy. Today we are joined by guest Richard Adamson. Richard is CEO of Industrial Climate Solutions, overseeing the development and commercialization of products based on the pulse-enhanced froth technology. This platform technology intensifies processes, reduces costs, and eliminates many constraints in gas or liquid contacting in industrial applications, ranging from CO2 capture and conversion to fertilization production to flue gas scrubbing in stationary and marine applications. On February 1st, 2022, ICS was acquired by Baker Hughes Turbo Machinery Process Solutions. Richard has 4 decades of experience in the development, commercialization, and marketing of commercial and industrial process equipment, technologies, and business models. He was the founding president of Carbon Management Canada, a network of centers of excellence and CMC research institutes. Before that, with Southern Research Institute in Durham, North Carolina, he helped establish the Carbon to Liquids Development Center. Now let's get into the episode with Richard. Welcome back, Dave, John, and Richard.
Good to be back.
Great to be here.
And as you can see, John's still in Canada, so...
Still in the same room.
I think this is our last episode with both of you in the same room, so we have to savor this one.
It is that.
It is.
Very much so.
Well, I'm really excited about today's episode. We'll be talking about industry implementation of carbon capture, utilization, and storage. Dave, I'll pass this on to you to kick us off.
Okay, thank you, Lysandra. And Richard, again, thank you for being our guest here. I think I wanted to pick up on something that I touched upon, well, you actually initiated this, is to discuss how this whole technology and the utilization of carbon, how that can be used or being productive or helpful in this for companies or industries.
Yeah, so there's a couple of reasons why it's important, and a couple of reasons why we need to maybe clarify the role of utilization. So we were talking before about carbon capture and storage, where we're primarily geological sequestration, deep geological sequestration, and the scale of those plants can be very large, and we can build them out for huge impact rapidly. The challenge with utilization is, first off, you capture the CO2 and you convert it into something that's got an economic market generally. So you have to be able to then sell it. And usually there's something else out there in the market that you're competing against. And so it takes time to drive, gain market share. So there's kind of a time constant involved with being able to penetrate the market on it. And there's also very, very few things that, for example, as a comparison on a CCS plant, there's very few products that you would use 1 million tons a year of CO2 to produce without basically swamping the global market. So there's a tendency to say, great, why don't we just make, and I actually saw this example, we can convert CO2 to omega-3 fatty acids at $20,000 a ton. Well, the economics are great, but how many gigatons of omega-3 fatty acids does the world market require? There's kind of a trade-off there. So I'm a really big booster of carbon utilization. I think it's got a role to play. The economics are so much better for that than storage. Therefore, we should quit storage because the scale is just not there, and the rate of penetration is not there. That's not a reason not to do it, but that's a reason not to say that's the solution. So there's a few questions there. There's some products that have a high economic value. So things like carbon nanofibers and exotic materials and things like that people are focusing on. And those have got good economics. Not massive volume, but good economics. And there's also a significant amount of effort to increase the market size for those by folding those kind of products into, for example, fillers for plastic injection, fillers for cement or concrete production, and those kinds of things. That's great. On the other end, you've got things that you actually need a lot of volume of. As an example, there's one group that I'm aware of that takes concrete rubble, leaches the old cement out of the concrete rubble, recycles the aggregate, puts it back on the market, but then they react their solution from the the cement with flue gas and make a synthetic limestone aggregate. So they make aggregate, they recycle aggregate, and they make money out of reducing tipping fees, basically tipping fees for dumping the concrete rubble that they're recycling in this process. So it's a win-win all the way around, and their economics actually make sense because in California, they import their aggregate from British Columbia and Mexico, and you don't just have a hill in your backyard you can dig aggregate out of, which in Alberta we have, so the market model may not work as well here. But so there's a range of different types, some that are very high volume, generally a lower dollar value, and some that are smaller volume and higher dollar value. And there's a lot of exploration going on. How big a role can these play? Important, interesting, but not instead of carbon storage.
Got it. So if I could, because you're going down this pathway then, so which industries are more likely to implement the CCUS?
Well, yeah. So there's a couple of drivers. There's industries that have large emission volumes that are a concern, and there's industries that are highly motivated to eliminate emissions for marketing reasons or ESG reasons or whatever, as opposed to simply the carbon taxes or fees or whatever they're facing, penalties. The easiest place to do carbon capture and storage has the highest concentration of CO2 in the flue gas. In fact, at the limit of that is, for example, bioethanol plants, because the process of producing bioethanol produces nearly pure CO2. So your capture process is almost done for you. So those plants will be really no-brainers because the cost of capture is very low. The cost of capture is very tightly tied to the concentration of the CO2. If you have, say, a hydrogen plant where you're making blue hydrogen, converting natural gas to hydrogen, you might be dealing with 20% or higher CO2 concentrations. It's a lot easier to capture CO2 out of that than, say, out of the atmosphere, which is 400 parts per million. And that's so looking at the concentration of CO2, that's one factor. The other is how much other stuff is in the flue gas. So capture off coal-fired power plants is challenging. It's the CO2 concentration is about 12%, not bad, but you've got a lot of ash and particulate and sulfur and maybe mercury, and so you've got to do a whole bunch of cleanup before you get to the CO2. The good news is if you're committed to doing CO2 capture off the back end of a coal plant, your emissions are really good off the back end of it because you've had to clean absolutely everything out of it before you get to the CO2. But on the other hand, it makes the amount of upfront work higher. Then you work your way down the scale towards, say, natural gas combined cycle power generating station. It's 4%, 5% CO2. That's harder. If you think about it, you now have to deal with comparing against that 20% CO2 range. You now have to move 5 times as much gas through your capture plant per ton of CO2 captured. So the size of your front end equipment goes up, the size of your blowers and fans goes up, the amount of electrical load penalty for all of that drives things up. So the lower your concentration, the more of that. So that makes it more challenging. On the other hand, the flue gas is really clean. You don't have any of that other nonsense to deal with that you do at the coal-fired power plant. So there's all kinds of interesting work on how do you address that problem as you move down. So really, that spectrum of concentration is really important. Direct air capture being the extreme hard choice. At 400 parts per million, you now have to have 100 times as much gas as you would from a natural gas combined cycle plant for a ton of CO2. So that's a really hard problem to deal with. So that's one set. And then, as we were talking before, what do you do with the CO2? So if you've got plants that are at the shoreline in Europe, where a lot of the carbon storage is marine transport to get to the carbon storage from the Northern Lights project out of Norway, for example. Now there's cement plants all around the shorelines that are looking at carbon capture because they can now dump the CO2 into a ship and transport it off for injection offshore from Norway. Or they've got the option, they can move down to the Netherlands or the UK and participate in different carbon storage systems that way. So physical location is another factor to take into account.
Okay, I'm going to ask another one of those simple questions that's probably not got a simple answer. There would seem to be shall we say, a minimum viable size for a plant to have its own carbon capture and storage. Can you give us any sort of guidance on what that might be, so that helps us think about which particular sites might be best for it?
Well, again, the policies and regulatory, it makes location really important.
Okay.
And you said carbon capture and storage. So,
Yes, I was particularly looking at the storage one. Yeah.
so if you're located right on top of a good geological injection site, and your business encompasses all of the right things, so an oil and gas company, or a company that involves oil and gas and refining and et cetera, a vertically integrated player, then that makes sense. And the larger the better is pretty much it. You start looking at
Okay.
anything less than 500,000 tons a year is probably going to be avoided, because you can do better at 1,000,000 tons plus. Now, that's fine for that case. Where there's shipping options, like I said, marine or whatever, that might actually reduce that size. If there's a pipeline, a gathering system outside your gate, then it could be quite a bit smaller. There's some really interesting technologies that are being developed that are small modular technologies in the tens of tons per day, up to 100 ton per day capture levels for very compact and efficient modular kind of pre-manufactured, truck it in and deliver it to the plant kind of situations. That's great. If you've got a beverage plant next door that will pay you for CO2, super.
Yeah.
If you've got something, a pipeline nearby that you can dump the CO2 into, super. The what do you do with it now question becomes the driver.
I want to pick up on that because you just said something. So effectively, the CO2, you can have a food grade CO2 from this.
Absolutely. Yeah.
Okay, so that's because
And there's a lot of chemical processes that require CO2 as an input. So
Yeah, we tend to forget that, don't we? Because there was recently a CO2 production shortage, and I can remember there was a shock horror headline that beer drinkers might have a problem in getting beer because there was a shortage of CO2. And I think it's one of those things, isn't it, that CO2 is seen as the bad guy, and yet we forget that it has other uses.
Well, I want to go off. Richard, you may or may remember this, or maybe I didn't bring this up, but we work in the greenhouse industry. It's a significant part, and they are dependent on CO2 for production purposes.
Yes.
And so there's a massive market in southwestern Ontario that they'll make their own CO2, or sometimes they'll buy it. And so I don't know how far-fetched it is, but is that a marketplace that could be used in the future? Anyhow.
Well, it happens in the Netherlands already.
Yeah, it does. Yeah.
Okay. So I wanted to pick up from where John went, and that is, what is the current price tag? And I know I'm asking you how long a piece of string is, by the way. And what is the associated timeline to actually implement projects? And I recognize, again, the size of the project and how big it is will add to this. But if you can give a range for our listeners so they get a sense of what this is. And again, I will tell our listeners, I expect it might be, the price was only going to come down as you described. More and more people will use it. Technology will happen. But what is the current pricing and time frame, if you could share with our listeners?
So I was at an event about a week ago, and the discussion was, and there's always a broad range because it really matters. How much pretreatment do you have to do? How concentrated is the CO2? All of that stuff. So how many dollars per ton off of a bioethanol plant is a lot different from a natural gas combined cycle power plant. But the conversation is kind of in the $50 per ton range right now on good sites. I'm not talking about the bioethanol plants, but on good industrial sites, $50 per ton. There's companies that claim they can do a lot better. Maybe they can, and I don't know what the driving assumptions are always. But I think 50 is probably a number that's in the right range. For the capture side, you have to add, probably, if you're really close to good geology and all of that, probably have to add another 10 to 15 tons, or $15 per ton, for the storage side of it.
Now, has that dropped substantially from, and I said 2020 is when we actually had this. It may have been earlier, but it seems to me that pricing has dropped pretty significantly from the last time we spoke. Is that true, or is it just to get my?
Yeah, no, it was, I think the pricing was in the kind of $80 to $120 range for quite a while. And I think it's come down quite a bit since then.
Well,
But yeah.
It's nice to see prices dropping somewhere because that's not the trend.
Yeah.
I did want to come back as far as what expected time frame. This is not a simple process. I think you indicated. How much time does it take to actually implement a system like this?
Well, where?
Yeah, I guess that's the big
So
question.
how many years do you set aside for your permitting, regulation, and public engagement process?
Yeah. Okay.
Forget the technical side, the engineering, all of that. You've got years of permitting and regulatory approvals and public engagement to go on before you even start the rest of the process. So yeah, it's really hard to put a number on it. Also, for example, in Alberta, we've built a few of those plants. We've got a carbon trunk line in Alberta. We've got a couple of capture plants. We've got a number of injection fields, deep sequestration, enhanced oil recovery. The groundwork has been laid with the policy and regulatory folks, so they aren't going to be surprised by this stuff when it comes across their desks. Whereas if you were trying to do the first of a kind in Ontario or someplace, you might find that the policy and regulatory people are a little more caught flat-footed, and we'll have to go back and do a bunch of homework, and so it could take quite a bit longer. So I'm sorry to dodge the question, but
No,
there's just huge variability.
I rightfully so, and I think it's important people.
Well, can we put a supplementary to that then? If you've got all the regulatory stuff in place, what would be the technical time scale?
Well, again, size matters.
Yeah.
I would say probably for a small plant in the 100-ton a day range, 100 to a couple of 100-ton a day range, you could probably get it done in 5 years.
Okay, that helps. That's interesting. Yes.
But larger, you go to the 1,000,000-ton a day plants, and it all boils down to people. It's not the technical is not the issue. The issue is, for a corporation large enough to be able to fund a 1,000,000-ton a year plant, what are their internal decision-making processes to get it to a final investment decision required? And getting through the bankers and the lawyers will dominate the process.
Yeah.
Geez, that scares me right away there.
Does this not speak to what you said, I think, in our previous podcast, that you need to get on with it now? Because if you've got these kind of lead times and everything else, it's only going to delay things further, isn't it?
Exactly.
Yeah. You might just have covered this, but just to put it into a nice thing, could you perhaps just talk us through an example of a current CCS or CCUS project that's in place?
No, there's a few of them.
Don't breach any confidentiality or anything, but
No. Well, I'll talk about existing built full-scale plants. There's a few of them in Canada. There's the Boundary Dam coal-fired power plant in Saskatchewan. So that's over 1 million tons a year capture capacity. That's CO2, and they do all of the things that I talked about, the challenging flue gas cleanup before capture, and then the capture side. And most of that CO2 is used for enhanced oil recovery and injected into oil fields. Happy to talk to you about the benefits of enhanced oil recovery and why it's not as evil as people say. That's a good example. In Alberta, we've got the Shell Quest project, which is over 1 million tons a year capture off of basically the hydrogen unit on a refinery at the Scotford refinery near Edmonton. There's also the Redwater Upgrader refinery, which was designed from scratch as a capture facility. So the design on their hydrogen unit was specifically designed for CO2 capture rather than being bolted on the back end. They, along with the Agrium fertilizer plant, are the core CO2 suppliers for the Alberta Carbon Trunk Line. So there's a few different cases there, and the Alberta Carbon Trunk Line also runs down to where its main user is for enhanced oil recovery. I'm going to take a little detour to talk about enhanced oil recovery, because people have an idea that enhanced oil recovery is a bad thing because it results in production of oil, which results in more emissions. As it stands today, CO2 for enhanced oil recovery is an input cost for the oil field, for the producer. Therefore, they're motivated to minimize the amount of CO2 that gets injected, and the oil that's produced when burnt as a fuel would result in more CO2 emissions than were injected. But if the incentives were set up so that the cost of CO2 was negative, the more CO2 you stored, the more revenue you generated, you can optimize that process so that actually you're injecting more CO2 than would be produced by burning the fuel that's produced by the plant. In some cases, you can actually do it as the oil is being produced, but at very least, by after you stop producing in the field, continue to inject for a few years, because you've already paid for all of the infrastructure and capital equipment. It's very minimal cost to continue to inject after production is stopped. So you can actually wind up with, and I know people don't like the concept, but it actually winds up being net negative emissions on the oil that's produced. It's just that right now, historically, the CO2 has been a cost rather than a benefit.
Comes down to the money, doesn't it?
Yeah.
Before we end off this episode, I do kind of want to conceptualize what a ton of CO2 is. So just giving everyone a figure from online. A ton of
Wow.
CO2 is the average emission of one passenger on a return flight from Paris to New York. It's also driving 6,000 kilometers with a diesel car, or around 3,700 miles. If you're into electricity, it's about 4,300 kilowatt hours of power consumption. But again, that depends on your jurisdiction. So that gets a little bit messy. But for me, listening to 1 ton, I'm like, I have no idea how to think of it. The return flight from Paris to New York helps me conceptualize what a ton of CO2 is. So thought I'd throw that in there.
I'm not going to comment on that.
Oh no, John.
You probably shouldn't. You probably should.
All right. So based on the information shared today on industry implementation of carbon capture, utilization, and storage, what is the biggest takeaway for our listeners?
Well, I would say it's the same thing as we talked about before. If you've got an opportunity to do it, do it. There's, as much as there may be some cost savings, the next generation might be a little bit more efficient. The tons of CO2 that are emitted between now and the next milestone mark in cost or whatever are going to be in the atmosphere for centuries. And the cost may not necessarily come down. Supply chains are going to get stretched as we build more and more of these plants out, and the length of time, the lead times on equipment and permitting and regulation and et cetera are going to go up. So I think that there are real advantages to moving early. The technologies are not as risky as they were originally. We're no longer dealing with first of a kind plants. The technology is proven. Let's just get out there and get them implemented.
Richard, if I could follow up, if a industry leader is listening right now and they're interested in implementing carbon capture, utilization, and storage, what are some steps that they should take to do that?
Well, there are some really good people out there to deal with, both on the consulting side in terms of understanding what's required to do a high-level assessment, preliminary assessment. You don't have to go to a vendor of CO2 capture equipment and cross your fingers and hope you got the straight goods. You could go to any one of a number of consultancies that work in this space that can lay out not just high-level numbers, but where the cost drivers are for your particular situation. There isn't a book you can look it up in, because it's completely dependent on a particular case, the particular emission source, your location. And as I keep coming back to, what do you do with the CO2? If you've got an opportunity, if you can answer that, what do we do with the CO2 question quickly, then you're halfway home.
Dave, John, anything to add?
I'm just going to add one. It struck me when you've said a number of times, what are you going to do with the CO2? it's very similar to another technology, which is heat recovery. And a lot of people look at heat recovery and go, oh, we could recover heat from this. I've done projects where they've said, oh, we want to recover the heat from that. And then you say, and what are you going to use it for? And, finding the use. And I think that, perhaps one of the takeaways for people is, do you have a potential use for CO2? If you do, perhaps you should start thinking about whether capturing it is something you could do.
Do you or your neighbors?
Yeah, fair point. Fair point. Yeah, because this is one of the things, this is a technology, it's like district heating, isn't it? You need a number of participants to really make it work well.
We didn't talk about it, but this concept of hubs and clusters, which the UK, by the way, is really leading in and doing a brilliant job on. This concept of hubs and clusters is going to be a really important one. So it's often not a single company decision, but is there a cluster of companies together where jointly the economics make sense, where an individual play may not?
Yeah, and I'll just feed off that. And speaking with David Lizelle, he echoed the whole idea of, because we work in the cement industry, he goes, not only should you try to get the cement industry together, but you should get the cement and the steel industry in the same room, because effectively they both have to do some things there. And if you can have the aggregate of them involved, you can make good things happen.
Because people sometimes forget, the thing about cement is, even if you fueled the cement process with totally renewable fuel, you would still have CO2 emissions because of the process.
Only about a third of the emissions are from the fuel.
Yeah.
So what did I pick up? Well, since the last time we spoke, certainly it seems like the pricing has dropped substantially. Sounds like the technology is changing and improving. And again, I should know when the last time we spoke, Richard, but I don't think it was like maybe 3 years ago, maybe 4. But it's changed dramatically. And you also mentioned something. This is not just for heavy industries like the steel and cement. There could be industries that could be motivated in the food industry that could be working in this capacity.
Well, and in Europe, I mean, what drives things are different here than in Europe. But in Europe, waste to energy plants, they invested heavily in putting waste to energy plants in to get rid of landfills, which is great. But now they've got all these emission sources, and they're now big push to put capture on waste energy plants, but even suppliers to the car industry. So it's great. The car industry is moving towards selling electric vehicles, but they also want to be able to look at the upstream, their supply chain emissions. So if you're a supplier to the automotive sector, maybe it's worth more than the dollars per ton tax rate for you to put capture on your plants in order to be able to be an attractive vendor into the supply chain. So there's some of those factors. Things are getting a little more interesting on some of these other factors.
Very much so. And like in Canada, when we're paying what we're paying per ton now, and it goes up $15 every year, it makes it much more economical every year to do this. So the summary is, and you've said it, is we need to get at it, and let's not waste time, because there's things that have to be done for the future that by waiting is not helping anyone. So thank you, Richard, for your time. I really appreciate it.
Yeah, thank you.
Well, thank you. It was a great pleasure.
That's all for today's episode of the 360 on Energy and Carbon podcast. Thanks for listening. Make sure to check us out on our website at 360energy.net and follow us on LinkedIn at 360energy Inc. Tune in to our podcast on Apple Music, Spotify, Anchor, or other listening platforms by searching the 360 on Energy and Carbon. You can watch the video recording and subscribe on YouTube at 360 Energy Inc. Email us your feedback at podcast@360energy.net or comment on our LinkedIn posts. See you next week.